Cross-validation is useless and merely an academic vanity exercise in the era of big data. What would be your reaction if your interviewer was making this statement during your job interview? Would you argue or would you agree with it? Hello and welcome back to my Applied Data Science channel. For those of you who are new here, my name is Joanna and I'm a senior data scientist. In this video, we are going to practice looking at the problem from two perspectives, because these types of statements have multiple purposes. For one, they want to test if you are very familiar with the concept that they are raising, and then on the other hand, they want to see if you've been reflective enough to think about a potential problem from multiple perspectives. But first of all, let's set the common ground for what cross-validation does, and then we will jump into pro and con arguments. A model learns from examples, and its purpose is to extend and extrapolate that knowledge that it learns to new unseen data set. In data science, a way to simulate this scenario is to split the data set in two. The majority of the data points are going to be used to train the model to build that knowledge about the intricacies of the data set, and a small part of the data which was not used for training is going to be set aside as unseen data, treated as new examples on which we are going to assess the model's performance, its capacity to generalize. Splitting the data in train and test is also called holdout. The goal of cross-validation is to set real expectations on the performance of the model in real world, on unseen new samples. Cross-validation starts from the premise that splitting the dataset only once into training and test is not sufficient, because that split could be the ideal one, or the unrepresentative split that is going to return the best performance of the model. For this purpose, the suggestion is splitting the entire dataset into multiple chunks and then building training and test sets from those chunks such that the data points are not overlapping, so they are not both in train and test. This way, we are going to train multiple models and we are going to run multiple evaluations of those models, resulting in multiple performance metrics. Ideally, we would have consistency in terms of performance across all these splits. Not only would this eliminate what is called the selection bias, or this risk of having the ideal split of our dataset, but it would also help to identify and prevent overfitting, a very common problem in data science. Don't forget to subscribe to my data science channel if you find this video interesting. And now let's jump into why could we possibly agree with this statement. If the unrepresentative split might happen when working with small and medium-sized datasets, is it even a risk when working with big data? I argue that a single train-test split, known as holdout, is sufficient due to the nature of big data and its three main characteristics: volume, variety, and velocity. When we have a diverse representation of the data both in train and test, which is very likely when we have huge amounts of data, we are just making the sample bias look neglectable. Secondly, let's address overfitting. Overfitting concerns are also reduced when working with big data. Overfitting occurs when the model that we are trying to fit on our dataset is too complex for the relationships in that dataset. But with large amounts of data and diversity, all those intricacies and relationships between data are becoming much more complex, so overfitting becomes less of a risk. Moreover, going back to a single train-test split, overfitting would become obvious if the model is performing much worse when evaluating it on the test set than it does during the training phase. Thirdly, adding cross-validation to your data science workflow, which is already a complex process for the data scientist, is adding on to this complexity even more. Remember that cross-validation's purpose is not to choose the best model of those that you are training. It's just to obtain a robust metric of how the model is going to perform on unseen data. There are easier methods with which we can achieve that. For example, a simple train validation test split known as holdout, or if we are working in the field of deep learning, setting an early stopping parameter. So now let's address expenses. In k-fold cross-validation, you would need to train a model k times, and imagine that you are working with deep neural networks and big data, so now all the expenses and the costs on using GPU machines are going to increase k times at least. So data science would become both financially costly and time consuming. I am going to play the devil's advocate now and tell you, you cannot go through life being that optimistic. If the unrepresentative split is something that is very unlikely to happen, you cannot just ignore that it might happen sometimes. Like tsunamis and earthquakes also happen even if they are very unlikely, rare events, and when they do, they shake up and impact people massively. We as data scientists must do everything in our hands to prevent sampling bias from happening. And addressing the second point now with overfitting, variety doesn't exclude data imbalance. And data imbalance is a common problem when working with big data. Overfitting is favored when we have data imbalance because the underrepresented class, even if misclassified, is not going to matter enough in order to impact the performance metric visibly. Therefore, overfitting is not automatically eliminated when having large data sets that are diverse. If overfitting was not a real problem, then why would have been techniques such as data augmentation been invented? Even in the era of big data, overfitting is still a problem that has to be addressed. Let's discuss reliability. Robust and reliable models need thorough evaluation, and while holdout might be the easy and quick solution for evaluating a model on unseen data, I'm just asking you, would you take a drug that was only tested on one patient? Remember that AI and data science is not just about classifying iris flowers, it is sometimes about playing with people's lives. So choose whether you perform cross-validation or not based on the project that you are working on. Why not prioritize quality over quantity? There is a lot of skepticism already around the adoption of AI, so compromising on quality just because it costs time and money is not the way to go. We as data scientists should for sure not compromise on quality just because we need to get a lot of products, no matter their quality, out on the door. Let data science provide reliable solutions. What is your opinion? Is cross-validation useless in the context of big data? Would you argue or agree with your interviewer now? Let me know your thoughts below and subscribe to my channel for more thought-provoking ideas and hands-on applied data science tutorials. I hope to see you next time. Bye bye!